So in this second video, we are going to continue to take a look at the hydrogen atom at first, and then we'll expand and take a look at some other things. But the emission spectrum for hydrogen was known to scientists. It looks like this. Now this purple line here is really not visible typically to the naked eye. So they created this from I don't know where. This is actually not an emission spectrum. This is just something that they created because that purple line is a little too close to UV for us to be able to see normally. So hydrogen typically has four lines: the red, the tealy color, and two like indigo, purpley, bluish colors. And this is known as the Balmer series because Balmer was the first one to kind of point out the lines exist, to be able to determine that those wavelengths are what you see there. And those are the only four lines for hydrogen visible to the naked eye. And so he was able to come up with an equation that was eventually known as the Rydberg equation, which you can see here. Where RH is the Rydberg constant. It is specific to hydrogen. And the integers N1 and N2 are really the different energy levels. And in order to figure out the wavelength, lambda, and not make it a negative value, N2 needs to be a higher energy level than N1. And so then that will give you a positive number in your answer. If you flip-flop these and make this one the bigger one and this one the smaller one, the only thing that's going to change is you wind up having a negative value. So it's really not that big of a deal, but that's typically what is done conventionally when you use this equation. So this lets you relate the wavelength to the different transitions in the hydrogen atom. So let's do an example. What electron transition from n equals 5 would emit a wavelength of light of 3,740 nanometers? So remember that in order to emit light, the electron is going from high to low. So emission happens when the electron returns to a lower energy level. Absorption happens when the electron moves up to a high, these are absorptions, moves up to a higher energy level. So what are we going to do? We're going to use the equation. We have the wavelength in nanometers. We have n equals 5. We know that this is emission, so we want to know what n equals 1 is. So we're going to set up the equation. Now notice that this is nanometers. We need to use the Rydberg constant in meters. So that's got to be our setup. And N1 is our unknown. So when we do this math, we come up with a value of n equals 4. So the transition that gives you that wavelength is between 5 down to 4 as far as the rings go. There's another equation, another modification of that idea that you can use, and that is how do you calculate the energy. So we calculated the wavelength in the last equation. This equation lets us calculate the energy value of a particular ring or level in the Bohr model. Now this isn't really useful because you can't stick a little probe in there and figure out what the energy is, or you say, okay, so what? So energy level ring 5 has this much energy. What does that do for me? Really nothing. It's the transitions that are really important. It's the changes in energy that are important. So we're going to take this modified equation. So notice that this equation has three constants in it: Planck's constant, the speed of light, and the Rydberg constant. So these three all combine to give you this value. So rather than having to worry about these three, we just kind of stick this number in there because that's the result of multiplying those three constants together. All right, so it's like I said, it's more practical to measure the change in energy during an electron transition. So that equation we're going to modify a little bit. So we've got the Rydberg equation or the Rydberg constant along with Planck's constant and the speed of light, times the transition between two energy levels is going to give us our delta E. So it's the equation but modified a little bit to give us something a little bit more useful, because we can see the transition via a color and then we can measure the energy of that transition. So if the transition is an emission, so if you're going from high energy to low energy, the value you should calculate will be negative. So if this is your starting point and this is your stopping point, if it's an emission, this is going to be a higher number, this is going to be a lower number, so you wind up with a negative value here because this is negative. If you have an absorption, energy has to go in, so delta E is going to be positive because you're starting low and going high, which winds up making this value negative. So a negative times a negative gives you a positive. Okay, so that's just something to help you kind of keep track of any calculations that you do. So let's practice a little bit. So we've got three transitions. Putting numbers into that equation, what would I wind up with? What's the energy change? Now, you can't predict which one's going to be the biggest because none of them are really a good comparison between each other. They're not all starting at the same place or ending at the same place. So if we put the values in, this is how you would use that equation. The delta, technically it should be delta E. So the change in energies of the three transitions, notice that the smallest jump from 1 to 2 is actually the greatest amount of energy. So that's a little interesting with that going on there. Okay, so can you use these Rydberg equations for more than hydrogen? Well, the answer is yes and no. You can use it for anything that only has one electron in it. So He, Li2+, He+, Li2+. But the value of the Rydberg constant would change a little bit, so you wouldn't use the negative 2.18 number. You'd have to have a different number here, but technically you should be able to use it. Who goes around looking at helium ions and lithium ions that have only one electron in them? Not many people. So as far as we're concerned, it's only good for hydrogen. All right, what are the problems with the Bohr model? So it only works for hydrogen, we know that. There's also no good reason to use a circular orbit, like Bohr said. You know, planets orbiting the sun, going around in a circle or an oval type orbital. So it's really a mix of different kinds of classical and quantum physics, and it just doesn't really work. But what we can do with it is use it to explore the idea of the photoelectron effect, which allows us to calculate ionization energies. We will get into that a little bit later. All right, so let's examine this quantum model a little bit more closely. So Bohr said there were rings. The quantum model said, nope, the electron cloud is way more complicated than that, if you remember. So what are some of the ideas that the quantum model lets us take a look at? Well, we know that electrons now have kind of this dual nature. Electrons act like a wave because they can have a wavelength and a frequency and so forth, but they also act like a particle because they do have mass, and so they can be influenced by forces upon them and so forth. So one of the first gentlemen to do any contribution to the quantum model was a guy named de Broglie. And he used the fact that electrons can bend light. Electrons can cause constructive and destructive interference with waves and so forth to come up with this idea. So the fact that electrons will behave like waves, they do everything that waves will do. They will add it together, they will subtract from each other and so forth. And he also used Einstein's equation in order to determine that what the wavelength of small particles would be. So the de Broglie equation actually is this one. You've got the wavelength is equal to Planck's constant, h is still Planck's constant, divided by the momentum, or mass times velocity. So how would we use that? It's really only, oh, there's all the ideas. It's really only useful. There, I did it again. It's really only, I keep forgetting to get rid of equations. It's really only useful for small particles, but let's take a look at what would happen if we had a big particle. Okay, if traveling at equal speeds, which of the following would have the longest wavelength? An electron, a proton, a neutron, or an alpha particle. Okay, so think about mass. Electron is really tiny, much smaller than these two. An alpha particle is 4 of these two combined. So look at Planck's constant. As the mass increases, the wavelength is going to decrease, right? It's an inverse relationship. So as the mass gets bigger, the wavelength is going to get smaller. So which one's going to have the longest wavelength, the biggest wavelength? The electron's going to have the biggest wavelength. Second question, here's the answer to it. What if we do look at something that is tangible to us to see, like a car? So what's the wavelength in meters associated with a 1,000-kilogram car traveling at a speed of 25 meters per second? Well, look at the wavelength that's associated with that. That's so incredibly small. It's like, why bother? There really is no need to measure a wavelength associated with a particle like that. So just working your way through this, remember that joule is kilogram meter squared per second squared. So substitute kilogram meter squared per second squared in here. Kilogram is going to cancel out. Meter is going to cancel out one of them. And then you have seconds canceling and another second canceling. So the seconds and the seconds squared will cancel there. So it works out that we actually do get a length. Gosh darn it. The Heisenberg uncertainty principle is another idea that has contributed to our understanding of the wave mechanical model. So Heisenberg said you can, with something so small, you can't know both the position and the momentum of the particle. And so these equations are in here to, more than anything, to impress you. It's the equations that are associated with the Heisenberg principle. We don't use them for anything. But it's just the idea that you can't know where something is and how fast it's going simultaneously for something that is so small. So for an electron, which has a very small mass and moves really fast, predicting its location is basically impossible. That's what the Heisenberg uncertainty principle is saying. Oh, and there are what the units mean. Oh my gosh. All right, so let's take these ideas from de Broglie and Heisenberg and combine them into something useful. Okay, if we look at the structure of the electron cloud, it's going to be different than Bohr's orbits. The wave nature of the very small, very fast-moving electron results in a model that lets us describe the energy of the electron, but the location becomes a probability, right? Because you can talk about speed and you can talk about location, but you can't talk about both simultaneously. So this is what led to the idea of the quantum model and the orbitals being probability maps. Remember, that's one of the things we learned in first year, that orbitals are probability maps of where you're likely to find an electron 90% of the time. So the quantum model is what we're going to take a look at next. But I'm going to quit the video here. I know this is really long. You can watch these in parts. Quit the video here and we'll pick up in part 3.